Hi, welcome to Renewable Power Generation Technologies. We were discussing the renewable energy technologies and their performance. So we will, in this discussion lecture, we will look at the performance analysis of the solar and the wind, right? Focusing on the horizontal axis wind turbine, the vertical axis wind turbines, then the photovoltaic systems and the solar thermal technologies. Okay. So we will start from the wind energy systems. So if you look at the wind energy system, uh, so you know that the wind turbines are the devices that converts the kinetic energy from moving air into a mechanical energy, right? So and then this mechanical energy can be transferred to the electrical energy by using the generators, right? So you use the induction machines like double fed induction machines and so on in the wind turbine in order to transfer the mechanical energy generated to the electrical energy, right? So we are focusing on in this discussion. Actually, we are not focusing on how the technology works, but we are focusing on their performance analysis, right? So you can see in the wind turbine, the main limitation is what we call the Betz limit, right? So this specify what is the efficiency of the wind turbine. So the Betz limits put a theoretical efficiency for the wind turbine, and it says it only can capture approximately 59.3%. So this is the maximum energy that can be captured from the wind by the wind turbine. So the energy can't go the beyond that, right? And yeah, so and then for an example, if your turbine manufacturer said this is 85% efficient, the wind turbine, so what you can actually the real efficiency would be this one 59.3% into 0.85, right? So this is the real efficiency. So you can see that uh, there is a theoretical limit for the maximum energy that you can extract from the wind, right, in a wind turbine. And then there's a turbine efficiencies and so on, generator efficiencies and the all other stuff coming in. And with all those, you can see the efficiency of the wind turbine will be less than the 59.3% when generating the electricity. So we will discuss more detail about the efficiencies later, right? Talking about the wind turbines, there are different types of wind turbines, as I indicated at the very beginning. So you have the horizontal axis wind turbines and the vertical axis wind turbine. So first we will look at the horizontal axis wind turbines, which are the most commonly used type of wind turbines in the electricity generation. Okay. So if you have seen these horizontal axis wind turbines, you know that they are very huge. Okay. In very early days in 1990s and 1995, they were very small, like maximum the blade uh, what you call it, the diameter is 30 meters, right? And it could only generate zero point 0.5 megawatt, but the technology has evolved over the time. And then by 2020, you have a wind turbine. You had wind turbines with the blade diameter of 125 meters, which can generate up to 5 megawatts. And in 2023, you can even find the horizontal axis wind turbines with uh, the blade diameter of 250 meters, which can generate up to 16 megawatts. And it is predicted in future you will have a larger wind turbines which has bed diameter of 280 meters, which can generate up to 20 megawatts. So they will be very large. So these are offshore wind turbines. And if you know about the technology, you have offshore and onshore and so on, right? So these are offshore wind turbines, so which are now larger than this rotor diameter, or the blade diameter will go up to 250 meters. Okay? And so since we are basically focusing on the performance of the wind turbine, so it's time to look at the performance matrices, right? These horizontal axis wind turbines, they have the capacity factor ranging from 25 to 45%. So if you're wondering what is the capacity factor, so the capacity factor is the unitless ratio of actual energy output over a given period of time, over a day or over a week or whatever, to the theoretical maximum electrical energy that can be produced over the same period, right? So this is actually you can say the actual energy produced, let's say E actual over E theoretical. This is for a given period. Let's say this could be maybe one month or 1 year, right? Something like that. Okay, for a given period. Okay, so this this basically indicate how well the system is running, okay, and how well it is producing the energy output. Okay. Okay. So in regions like Sri Lanka, in the certain areas like the Mena, you have the Mena wind farm, right? You can achieve the capacity factor around 40% at 100-meter the hub height, right? So what's the hub height is basically the height to this is the hub, right? So this is the hub height, right, of a wind turbine. So I believe you might have heard about these things before, the technical stuff, but so in this course we are basically focusing on the performance analysis, so please keep that on mind as well. Okay. And when you're analyzing the performance, there are various the factors that you need to consider. One is the one is the technology specific stuff, like these capacity factors, efficiencies, and so on. And the other one is the very important one when it comes to the real world implementation, is the financial aspect, right? And also you have to look at the environmental impact as well, so that is also very important, right? So if you look at the financial aspect, the horizontal axis wind turbines has improved very significantly over the time, and the cost per kilowatt hour generation has been reduced from $2,042 in 2010 to $1,325 in, this is should be kilowatt hour, in 2020, right? So that means the the capital cost and the operational and maintenance cost has been reduced considerably, making the wind project more and more feasible over the time, right? And it will keep on improving, so these technologies will be easy to implement, right? Even for the countries like Sri Lanka, right? And also the levelized cost of energy, which is basically talking about the cost of different the cost of different energy technologies over their lifetime, right? So representing the average cost per unit of energy produced. So you can say this is the dollars per kilowatt hour, right? So this is a levelized cost of energy. This incorporate all the costs associated, like the capital cost, operational and maintenance cost, and other different types of cost, and you calculate the cost per unit of energy produced, right? So you can see, if you look at the levelized cost of energy for onshore wind turbine is approximately $0.04 to 0.05 per kilowatt hour for the very recent projects. Okay? So that you can see that the if you convert this into rupees, approximately multiply by 300, so you will get I don't know, like 1000, right? Sorry, say 300, so you get 4 no 12 3 3, right? Yeah, about 12 rupees, right? If I make it correct, right? So it's low compared to the levelized cost of energy for the coal power plants and the other type of fossil fuel based power plants, right? Because the wind is free, the operational and maintenance cost and the capital cost is one basically dominating. So the what you call the fuel cost here is actually almost free, right? So it's the low rates. And if you look at the environmental impact, the horizontal axis wind turbines have very low carbon footprint of about 11 grams CO2 per kilowatt hour produced. Okay, and because the wind is very clean energy, and but though the carbon footprint is very minimal compared to the thermal power plants, uh, so they have some environmental concerns, like the visual impact, right? So when the blades are rotating, it covers the sunlight. So if you are living near the huge wind farms, you will see the flickers happening. It gets dark as the shadows, right? Shadows will flicker as the turbine rotates, right? So that's why, typically near the wind power plants, you keep certain gap between the residential areas and these wind power plants. So in order to make sure you don't get this the visual impact, right, which would be a little bit uncomfortable for human eyes, right? So that's one of the major environmental impact that creates by the wind power plants. And the other one is the wildlife, the birds and the stuff. So sometimes birds comes and hit, because they can't judge this rotational speed and so on, so they can't go through the wind blades, so sometimes they hit and die. So that kind of situations can also occur. So there are certain environmental concerns in the wind turbine, but if you look at the carbon footprint wise, it is very low, right? uh, and it's the overall impact is very significantly low compared to the fossil fuels, making the wind energy one of the most sustainable energy option available. Okay. Right. So let's look at the wind energy systems, or the vertical axis, the wind turbine. So here we talked about the horizontal axis wind turbine. So now if you are looking at the vertical axis wind turbines, there are different types of wind turbines that you can see in here, right? So you have 7 years type and the Darius type, the wind turbine, right? And the new technologies are coming, right? So the, as the name says, the different is they have these blades that are rotating in the vertical axis. So you have the vertical axis and then everything is rotating like that. Okay. So okay. Okay. So there are different types of wind turbines. As I said, the vertical axis, the wind turbine. So they have 7 years type and the Darius type vertical axis wind turbine, and they work on different principles. The 7 years type operates on the what we call the drag principle, and the Darius type relies on the lift principle. Okay. So each of these type has their own characteristics and their own pros and cons, okay, in different application. Okay. And if you look at the efficiencies of the vertical axis wind turbine, right, it is a little lower efficiency compared to the horizontal axis wind turbines, right. For an example, the lift-based the vertical axis wind turbine capture about 30 to 40% of the wind energy at peak efficiency, right? While the drag type ones are have very minimal technology the efficiency, which is about 15%. Okay. Okay, and if you look at the capacity factor of the vertical axis wind turbine, so they tend to be lower than those of the horizontal axis wind turbine. Okay, but we have limited data, due to the availability of utility scale vertical axis wind turbines. There are no much the utility scale vertical axis wind turbines. So these type of ones are basically really good for the urban areas and so on. So these are basically kind of distributed and the small scale wind turbine, not the large scale wind power plants, right? So because of that, it's very hard to compare them with the horizontal axis wind turbine. Okay. Okay. So if you look at the cost per kilowatt or kilowatt hour of the vertical axis wind turbine, so these are generally high compared to the horizontal axis wind turbine due to the lack of basically mass produced multi megawatt models. So you don't have a large scale models that are produced in a mass scale, right? So because of that, the capital cost would be the high. Okay. But the simplicity of the design of this type of wind turbines will have the potential of having a the cost advantage over the horizontal axis wind turbine. Okay. But we are yet to see the technology booming. Okay. If you look at the operational and maintenance wise, it is much easier compared to the horizontal axis wind turbine, because if you look at the horizontal axis wind turbine, they are very very, the height is one of the major problems. Now if you look at the here, now for an example, okay, this 251 into 2023, it has about 160 the meters hub height, right? I think it should, yeah, yeah, okay, like that, yeah. And then so the operational and maintenance would be much difficult at these levels. Everything, all the generators, gearbox and everything is in the in here. Okay. So somebody has to go there and do the maintenance, and it's little difficult to do the maintenance, so the maintenance cost to be much higher compared to the horizontal the vertical axis wind turbine, where the all the generators and everything would be in a ground level. Okay. uh, and also this the structure wise much simpler, right? So here you have the huge structure that should support everything, but in this case you don't have that kind of requirement, so the operational and maintenance cost would be lower compared to the horizontal axis wind turbine. Okay. The environmental profile, both the vertical axis and the horizontal axis has the very similar environmental profile. Okay, so having almost no emissions, and only the emissions that are associated is at the manufacturing of the blades and the other equipments, right? Not at the operation. Okay. So you have to encounter those as well. There are you can't say this is zero emission, because there are certain emissions during the manufacturing process, right? And that also has to be incorporated if you are doing a very thorough analysis. Okay. Okay, and these turbines will pose less risk compared to the horizontal axis wind turbine to the blade the birds due to their visibility and the shorter heights, right? So the birds can go over, right? And okay, but yet to be proven, because we don't have a large scale wind farms using the vertical axis wind turbines. Okay. And this will be, as I said earlier, very suitable for urban or suburban environment. Okay. Where the wind direction is the variable, due to various reasons, due to obstacles and various other things. In a horizontal axis wind turbines, you have to have the wind in more or less the same direction or the similar direction, so you can only rotate this to a certain amount, and then face the wind, and you can also rotate the blades to get the maximum efficiency a little bit, but there's a limitation to this, so you expect wind to be flow in more or less the same direction here. But in this case, the direction of the wind can be variable, and this vertical axis wind turbines support this the variable direction, so they are very suitable for urban and suburban environment. Okay. Okay. And okay. And so if you look at the current market position, okay, so the vertical axis wind turbine currently occupied very small market, right, compared to the horizontal axis vertical turbines. Okay. Because they outperform the vertical axis wind turbines in terms of efficiency, capacity factor, and the cost per kilowatt hour, right? And there are continuous research going on in this area to enhance the vertical axis wind turbine design. Okay, so in future you may have a better high performance vertical axis wind turbines, okay, compared to what you have today. Okay. So that's about the wind technology, right? And so we will look at the numbers in details later on, right? Because our main focus is on the performance analysis, so the numbers are very important, right? So we will look at the numbers, and we will compare both the wind and solar and different technologies later, right? So before we go there, brief about the solar energy systems. Okay. There are different types of solar energy systems available in today. Okay. From which the photovoltaic systems plays the major roles in today's electricity generation. Okay. And also you have what we call the solar thermal conversion, which are basically used for water heating, as well as now there are modern technologies available for electricity generation through the solar thermal conversion. Okay. Uh, okay. Uh, so in the photovoltaic conversion, so we'll start from the PV or the photovoltaic systems. Okay. So the PV conversion or the photovoltaic conversion involves the direct generation of electricity from sunlight. I think you are very familiar with this technology. Okay. And we use what we call the PV panels or the photovoltaic panels made out of PV cells, right? And there are various ways that you can arrange these cells. So cells will create the modules, and modules will create the panels, and you can arrange these modules and panels in a way that you can get the desired voltage and the power output, right? So these panels will basically convert the sunlight into the electrical energy, and that will make them a vital component of a solar energy system, right? And this the among the solar panels, the flat plate panels are the most common type of solar panels, right? So they have the flat surface that collect the sunlight and converts into the electricity, right? And so you can install them in a rooftop, or you can even install them in the large solar farm, so what we call the ground mounted one, right? And you can also do the maximum power point tracking, so you can the rotate these panels in this way, and also the other way as well. So there are different the mechanisms available to follow the sun and get the maximum energy out of the solar panels. Okay. Then the solar thermal conversion, as I said, captures sunlight as a heat, right? Rather than producing the electricity straight away, right? Like the PV panels. Okay. So in the solar thermal, what you basically do is you capture the sunlight and convert this into the heat, right? And very basic utilization of this heat is to heating applications like water heaters and so on, and sometimes for cooking as well. And with the modern technology, you can also convert this heat into electricity, right, through the steam generation, making it a very good method to harness solar energy to produce the electricity, right? So we will look at these technologies in details soon. Okay. So this the one of the ways that you can convert the solar energy into the electricity is by using the non-concentrating the concentrating solar thermal solar power plants, right? And you also have what we call the non-concentrating solar thermal systems. They are basically utilized for the water heaters, and basically for heating purpose. Okay. And basically used in the residential and commercial applications like hotel industries and so on, in order to heat the water efficiently. Okay. But the concentrating solar power systems, they are basically use the mirrors to focus the sunlight into a central location, right? Which generate a very high temperature, and that produce the steam to drive turbines and generate electricity. So in this the one option is you have what we call the solar towers, and around the solar towers you have the number of mirrors in in all directions. I will show you in the better one later, right? And this will reflect the sunlight into a central location, so which generate the large heat at this point to boil the water, and then generate the steam in order to generate the electricity, right? So I'll quickly, I don't know, this is the one, such concentrated solar power system. So we will look at them in details the later. Okay. All right. So okay. So let's look at them one by one. So we will start from the solar PV systems. Okay. Uh, so as we discussed earlier, so this basically convert the sunlight into the electricity by using what we call the PV cells. Okay. Which are made out of semiconductor materials like silicon. Right? So there is a significant manufacturing process happening here, and also utilization of the what do you call certain I would say the, I don't know, right, whether I can say this is a non-renewable, but some the limited the resources, right, the silicon. Okay. So this can generate a significant power, right? You can you have utility scale installs capacities producing megawatts of power, under the optimal sunlight conditions. So you have what we call the solar farms, having a large number of PV panels and connecting together, producing the megawatts of power, right? But the one issue in the PV cell is they are low efficiencies. You can see that the PV panels, the efficiencies can range from 15 to 20%, right? And the PV cells which are under the research can achieve efficiencies up to 23%. So there are ongoing research happening on improving the efficiencies on the PV cells and the PV panels, right? But yet they are at the lower end, 15 to 20% at the commercial level. Okay. Okay. So now for an example, under the full sunlight, the typical PV panel can produce approximately 150 to 200 watts per square meter. So then the size of the PV panels and the number of cells and how many panels you have will determine the power output of the solar farms. Okay. And if you go for the rooftop solar, then you will have a small scale power generation, but happening in a distributed manner all over the country. So you might have heard about these things very recently, and there was a very recent power cut, and the most people to be blamed on the most people started blame on the solar generation, right? But due to the distributed scale, the nature of the solar generation in the country, some are visible to the Ceylon Electricity Board, and some are not visible to the Ceylon Electricity Board. So that was one reason for this recent blackout. But I don't know, like I am not the person that's going to blame on the PV generation to create the power cut, but there are various reasons for that. So the PV generation is very important to the sustainability of the country, because the energy cost is very low. The fuel cost is almost zero, it's free, right? And the countries like Sri Lanka, that's very important. But the initial cost is pretty much high in the solar PV. But this is very feasible and technology for countries like Sri Lanka, but you have to have a better infrastructure to facilitate the high penetration of the solar in the country. So the infrastructure, managing the infrastructure is also very important, right? Okay, so as I said earlier, we are not going to look at the technology specific stuff, but we are going to look at we are looking at the technology specific stuff, but more focusing on the performances, not the other stuff here. Okay. Uh, so if you look at the sorry, the capacity factor of the PV, okay, so it varies based on the location, right? How much solar energy you have, and also based on the system design. Okay. In a cloudy regions, the capacity factors can be low as 10%, while in the sunny desert like Africa and part of India and so on, they may achieve around 25% the capacity the factor, right? So if you forgot what's the capacity factor is, so it's basically the actual energy produced divided by the theoretical maximum energy that can be produced, right? So utilization, you can basically think about it like that. Okay, so the capacity factor is about 25% if you have a very sunny environment. Okay. So for an example, the Agua Caliente in the Arizona, the solar project, they have capacity factor approximately 29.1%. Okay. So you can see you can achieve high capacity factor when you have a nice sunshine and so. Okay. So what important to us is what is the solar potential in the Sri Lanka. So if you look at the solar potential in Sri Lanka, so in Sri Lanka we receive about average 4 to 6 kilowatt hours per meter squared of solar irradiation or solar insolation, okay, daily. Okay, and it's a very sunny country. Okay, and this can translate to the capacity factor around 15 to 20%, right? So for a well developed PV system. Okay, so you can see this is a very good location for solar energy development, so why not harnessing them. Okay. So we have to overcome various other technological challenges, like you only have the solar during the daytime, and what if the night time and the early morning, right? So we need to have energy storage systems or some other way to do the energy storage, like the pump hydro and so on, right? So we have to address all those technological challenge, but if you can do that, it's a very very good energy system for countries like Sri Lanka, right? So if you compare the energy yield, right? So what is the energy yield? So first of all, we will look at what's the energy yield. So energy yield refers to the total energy produced by the PV system over a specific period, such as daily, monthly, or annually, right? So if you look at the energy yield per unit area, right? Compared to the wind farm, in US solar farms, they have the energy yield between 35 to 146 kilowatt hours per meter squared per year. Okay. Okay. So basically averaging around 9 watts per meter square. Okay. And the world largest the PV park like Badla Solar Park in India achieved the yield of approximately 5 to 6 watts per the meter square. So based on the amount of solar energy available, right? Right. So as I said, one of the major challenge is the load matching challenge in the PV systems. So we don't have sunlight in the night or early morning. So there's no way that you can meet the load demand at this point, right, by using the PV. Okay, so for overcome that, you have to have energy storages. The one way is to have the battery banks, which are basically expensive, but you can go for other technologies like uh, well, like what you call it, the pump hydro. Okay, or you can even go for the hydrogen based technologies like fuel cells and so on, to store the energy, right. uh, Okay, so that's technological aspects, and if you look at the financial aspect of the PV system, okay, so you can see very significant cost decline from early stage to not early stage actually, compared to 2010 to 2020, right? So the cost of PV electricity has fallen dramatically by 85% from 2010 to 2020, basically due to the introduction of new technologies, right. And then okay, so during the same period, the PV module price has also fallen down, basically, due to advancement of technology. The PV module price dropped approximately 93%, primarily due to increased production scales and the improved efficiency. Okay, so research are still going on, for take the higher efficient solar PV systems. Okay, and if you look at the levelized cost of energy of utility scale PV, okay, so you can see by 2020, the levelized cost of energy for utility scale PV was about 0.057 per kilowatt hour, compared to the dollars 38 cents. Okay, so see, this is $5 approximately. This is $38 per kilowatt hour in 2010, right. It was very high in 2010, but now it has been dramatically reduced also, the levelized cost of energy. Okay, and the now the due to the advancement of technology and their outcomes, the competitive solar power purchasing agreements are there, right. So you can see very the competitive solar power purchasing agreement prices in the range of 0.02 to 0.05 per kilowatt hour, right. So this is when you trade the solar power, or when you sell the solar power to the utility, you have these attractive prices. So these prices were set up basically to uh, motivate the people to produce more and more solar energy and sell them into the grid, right. uh, okay, so this was very famous in Germany, right. So they have set up a very attractive price for buying solar energy when they started initiating the solar PV systems in the Germany. And and then more and more people start producing the solar energy, and there were large scale solar as well as the distributed solar. And then I can't remember exact years, at early 20, I don't know, about 2019, 18, or 2020, somewhere around that, they have lower the price, and the price was less than the selling price. The buying price was less than the selling price, but the people still use maintain the PV systems and so on. So that's a different story. Okay, and you can also see the capital cost, the one of the factors that you know basically decide how feasible the solar PV projects is the capital cost, because it's comparatively high, right, compared to the other systems. So the PV projects are approximately, 800 to $1,000 per kilowatt, right. And also this can be vary depending on the region and the other various factors, right? So the capital cost wise, the PV projects are in a high end, but the operational and maintenance cost, eh, range from $10 to $20 per kilowatt per year, okay. Because and it's, you can see it's in a lower part, right. It's a low value, basically due to the absence of the moving parts like generators and so on, right. So this will help to maintain the low levelized cost of energy, because though the capital cost is very high, the operational and maintenance cost is very low, and also the fuel cost is almost zero. So that will create the levelized cost of energy low, right. uh, and uh, and then the other factor that actually determine the feasibility of the PV project is the payback period, right. So the payback period basically determines the time taken for the investment to recover its initial cost to the cash flow in the generate in the system, right. So the payback period for these PV the projects are range from 5 to 10 years, depending on the size and depending on the availability of the sunlight and the location, and also depend on the local electricity tariff. So the payback period is in the quite okay, because it's range from 5 to 10 years, and compared to the long lifespan of the PV system. So you can see the lifespan of the PV system is around 25 years. So you get your payback, let's say within 10 years, and another 15 years you are basically earning profit, right. So due to the long lifespan of the PV system. So having a 5 to 10 payback period is a very good factor for the PV system projects compared to the long lifestyle. Okay. Uh, okay. So this the rooftop PV systems even have a shorter payback period because of the small scale and so on, right? Which making them more and more popular, but also giving a lot of other issues in the grid stability and the voltage regulations and so on, right? So you can look at them at your free time. So what are the challenges posed by the high penetrated the solar PV system, specifically these rooftop solar systems. Okay. And the PV systems also have very attractive return on investment. Okay. So the solar projects has become increasingly attractive, uh, basically when considering the subsidized or high retail electricity rates, right. uh, right. So then as I said, the other factor is the environmental impact. So if you look at the environmental impact of the solar PV system, so they have clean operation, so no greenhouse gas emission at the PV generation. Okay. Or no on-site pollution, making them an environmentally friendly energy source. Okay. But you have to keep in mind that during the production of PV cells and so on, they have they have certain emissions happening. Okay. And the energy payback time, which is basically the basically talk about the how long it takes to generate the energy equivalent to what it was used in manufacturing, right? So this energy payback time for the PV systems are approximately 1 to 3 years. That means they basically produce that the energy they have taken for the manufacturing process within 1 to 3 years, right? And the life cycle CO2 emission is about 41 grams CO2 per kilowatt hour, okay, which is significantly lower compared to the traditional fossil fuel cell based technologies like coal, which is about 820 grams per gram CO2 per kilowatt hour, and in the gas you have 490 grams CO2 per kilowatt hour. So it is very low compared to the traditional fossil fuel based technologies, right? One of the key environmental considerations in the solar PV systems is uh, okay. So they displace the local habitat. So if you go for the large wind farm, so you need a large area, so you have to have a open area, so that might displace the local habitats, okay. But the modern technologies are coming like the agrophotovoltaic or the agrivoltaic systems, so which kind of trying to what you call it, the trying to so you keep the agriculture while having the photovoltaic systems on top of them. So you have the your cultivations on the bottom, so it can be any, and then you have on the top you have this the PV systems, right? So you have certain enough gap, so the certain sunlight can go into your crops, and the crop yield and everything would be uh, you know will not damage much, but you also produce the electricity, right? So those kind of technologies are there, and you can also see there are transparent photovoltaic panels these days, so that can also be utilized to uh, you know uh, minimize these environmental effects, right? And also when you're considering the manufacturing of PV panels, though they require the materials such as glasses, aluminum, silicon, and certain critical materials, which basically raises a concern about the resource sustainability. Although the sunlight is sustainable, you don't know about these resources, so you have a certain concern about the sustainability or the availability of these resources for the future manufacturing. So you have to find different ways of harnessing this energy, okay. uh, okay, so that's about the solar PV systems. Then the other technology is the solar thermal systems. So as I said, solar thermal systems can be utilized to produce electricity as well as to basically for heating purposes, right? So there are different types of thermal collectors that are used for heating purposes. So you have the flat plate collectors like what you have shown in here, right? And you have also you have uh, the evacuated tube collectors, what I have shown here, right? uh, so these are basically used for applications like water heating and space heating, right? So these are very familiar in Sri Lanka as well to produce the the hot water, right? and in the countries like Germany, so you still have the space heating that are done through this kind of arrangement, right? uh, So this the efficiencies of solar thermal systems are quite higher compared to the PV system, because but keep in mind we are not talking about the electricity generation, just the water heating. So the efficiencies range from 50 to 70%. Okay. Uh, okay. So and then if you compare with the PV efficiencies, the PV efficiency generally achieves around 20% efficiency in converting sunlight into the electricity, but the solar thermal can capture about 60% of solar energy as heat, right? uh, okay, but when you convert it to the electricity, that efficiency might also drop a little bit, but as a water heating, it has a high efficiency. Okay. uh, okay, so you can use the solar heating to efficient load matching, right? So particularly in the applications like you heat the water during the daytime, and you can store them in a tank for later use, right? So you can even have a hot water in the night, right? And which will basically minimize the energy losses and maximize the efficiency, right? And the capital cost is also in a bearable value, right, for the customers. So even in Sri Lanka, so it's not the cost is not that high to have a solar thermal system, right? And the payback period is typically around 2 to 8%, depending on the size and the other factors. And the shorter payback period for even especially for small scale will you know uh, will what do you call it the will make this technology more famous among the residential customers as well. Okay. So if you look at even in Sri Lanka, if you go into the many of the hotels, they use this the solar thermal systems to produce the hot water, right? So in the countries like Sri Lanka and the countries in South Asia, these the household hot water systems has approximately about 5 years of payback period, right? So uh, basically due to the high electricity tariff, right? uh, so your payback period is low, right? So this is much feasible solution compared to the electricity, especially when it comes to the water heating, right? And also the maintenance requirement is also low in this solar thermal systems. Okay. and and also the levelized cost of energy, or the cost per kilowatt hour of solar heating, can be remarkably low. Okay. uh, so basically resulting almost free uh, okay, heat thereafter. Okay. uh, and the return on investment is also high, right? So the solar thermal system, they can yield to high return on investment over their lifespan of 15 to 20 years, right? uh, so after recovering the initial capital cost, it's basically what you are earning is the profit, right? Okay, so before we wind up this session, so we will briefly discuss about the concentrated solar power system. So you will have the idea about the all the different types of PV systems and the the solar systems before we wind up this session. Okay. So the concentrated solar power, if you haven't heard about this, so this what this basically does is it utilizes the mirrors or lenses to concentrate the sunlight, okay, producing a high temperature heat for electricity generation, right? So you can use these steam turbines to heat or heat engine to produce the electricity, right? So you use the solar thermal to heat the water and generate the steam, and those steam is used to generate the electricity. So there are different types of CSPs, or the concentrated solar power technologies. So you have the this is the one, the parabolic true collectors, right? So they use these curve shaped mirrors, and you have this pipe which basically the water is flowing, and then they get heated through the reflected sunlight, okay. And then the second type is the tower type that you can see here as well, the tower type, okay. So you use the mirrors, okay, to focus the solar energy into one place to produce the massive heat, okay. And the third one is the parabolic dish, okay. Okay, so you basically focus the sunlight into the receiver engine, right, and produce the heat over there. So okay, and then the fourth type is the linear type, right, or the linear Fresnel reflectors. So they use flat mirrors rather than curved mirrors to focus sunlight into a tube, right, containing heat transfer fluid. So you have the heat transfer fluid here, and you transfer the heat into this tube in here by using the flat mirrors at the okay. So those are the different technologies available for concentrated the solar power, right? The one advantage of this the thermal and the concentrated solar power system is the ability to store the thermal energy, right? So you store the heat to be stored in material like the molten salts, okay. So you store the heat in the molten salt, and you can later use them to produce the steam, right? So this will overcome one of the issues that we had in the PV system, and it will allow the concentrated solar power plants to generate electricity even after the sunlight, so which basically enhance the reliability of the system, okay. So if you look at the solar to electric efficiency, the concentrated solar power systems, they generally have efficiency of 15 to 25%, right? So in the solar PV system you had 15 to 20%. Now here you have 15 to 25% in the right. Okay, so it also depend on the technology. The parabolic true plane typically achieve around 15% net efficiency, while these the modern power towers, that those are the power towers that we talk about here. So they have the efficiency about more than 20%, right, and becoming more and more popular, right, specifically in a desert environment where you have the large land and the plenty of sunlight, okay. So the capacity factors for the concentrated solar power can vary very widely, okay. So without the thermal storage, the capacity factor may be around 20 to 25%, but however, if you have a thermal storage, it can be improved to 40 to 50%, right. So if you remember, the capacity factor is the actual energy produced over the theoretical energy, the maximum energy that can be produced. So you can see that the utilization of the energy can be improved by adding the storage, and you can take the capacity factor to 40 to 50%, right? For an example, in the Spain's this Gemosola plant, right, they have reached over 60% during the peak operational period. So this kind of a power plant, right? So you can see there are many towers in here. So you can see one here, the one here, and so on. So, and with the storage you can achieve around 40 to 50, and in this particular power plant it goes up to 60 during the peak operational period, right? And since we have the energy storage capabilities, so the load matching capacity also increases, so you can match the load even during the night time where you don't have the sunlight, right? So the one of the real world example is this Gemosola plant in the Spain, right? So it equipped like 15 hours of molten salt storage, right? And has achieved impressively about the capacity factor of 60%, showing that the potential of the concentrated solar power, right? But the one issue is this need more landscape compared to the I don't know, like solar PV. You have to work it out, the numbers, to see which one is more efficient, right? uh, so if you compare with the PV, the energy yield uh, uh, per unit area of the concentrated solar panel is comparable to the solar PV when considering the land used by the mirrors, right? So because this also need a very large landscape, right? uh, So for an example, this crescent dance plant with 1.21 kilometer square, right, of mirrors. So they achieve the energy delivery of approximately 500 to 600 gigawatt hours per year. Okay, translating about 50 to 60 kilowatt hours per meter squared per year. So that's the energy yield, right? Uh, Okay, so it's very depend on the size and the availability of sunlight. Okay, so if you look at the history of the concentrated solar power, it was traditionally been more expensive than the PV and the wind energy. Okay, but however, this things is shifting now dramatically. Okay, uh, for an example, now in the concentrated solar power systems, you have the levelized cost of energy declined by 68% from $0.34 to $1 per kilowatt hour from 2010 to 2020. So we will do the comparison between these and the other different energy generations later on, right? So you will see a very good comparison later, right? But despite of this reduction of the cost, the levelized cost of energy, the current cost still is however around $1 to $10 to $0.18 per kilowatt hour. Okay, so which remains a little high compared to the PV and wind alternatives. Okay. And the capital cost is also ranging from $4,300 to $5,000 per kilowatt hour, right? So you can see this is significantly exceeding that of the PV system, because the large infrastructure that you need these towers, and you need a large number of mirrors and so on. So this capital cost is also very high. Okay, and also these have higher operational and maintenance costs due to complex equipments and need for regular mirror cleaning, right? To keep the efficiencies, and so that makes the operational and maintenance cost is also high compared to the PV. Okay, so because of all these things, the payback periods are a little bit longer than the PV, so typically around 10 to 15 years or more payback period for this type of the technology, right? Okay. So the research is going on to improve the concentrated solar power technology, and in future there could be a significant cost reductions in this area. Okay. Uh, so lastly, we will look at the environmental impact, right? So concentrated solar power technology, they offer significant environmental benefits, including zero operational emissions, right? So no greenhouse gases, right? And very low carbon footprint per kilowatt hour when compared to the traditional fossil fuel like solar PV systems. Okay, and the uh, okay, so the analysis has shown that the concentrated solar power system has approximately 22 to 36 grams per gram CO2 per kilowatt hour, right? Which is significantly lower than the fossil fuel. So you have seen the numbers earlier, right? Uh, so what are the environmental challenges with the concentrated solar power is that they require very large land areas, right? Which are often suitable in sensitive desert ecosystems, right? And otherwise there would be damage to the larger habitats, right? And then also the concentrated sunlight near the power tower can be the pose a risk to birds, right? Sometimes causing fatal injuries, right? uh, and so this system also need the heat transfer fluid, right? Which are basically oil based. Okay. uh, so you need to carefully handle them and manage them, and the waste uh, and you have to handle the waste as well. Okay. So at the end of the lifetime, the decomposition of decommissioning of the concentrated solar plants, they involve the removal of considerable amount of materials such as steel, glass, and salt, and so on, right? uh, so fortunately these of materials can be recycled, so the glass, steel, and the salt, right, further reducing the environmental footprint of the concentrated solar power plant, right? uh, so overall it can consider to be environmentally friendly, okay, particularly in terms of emissions. Okay, however it is the land and ecological impact is a little bit high, right? And so it's same as what you required for a large photovoltaic and wind farms as well. You need a large landscape, and there could be other impacts to the habitats around it. Okay. All right. So okay, so that's basically discuss about the solar, different solar technologies and different wind technologies to the produce uh, the electric energy, right, or electricity. So next we will compare these technologies back to back. So we have had about more than 1 hour session, so I will pause the session at this point, and in this next session we will talk, compare these different technologies back to back. Okay. Right.